All right, welcome. So let's get started. Um, we had one meeting this week. We had the DevoWar meeting. And I wanted to share a couple updates on the DevoWorm group. So this is the YouTube channel for DevoWorm. And we got a couple of videos in the YouTube channel. We have our weekly meetings. So we have, I think since our last update, we had number 7, 8, and 9. These are just the weekly meetings. So last week we talked about this paper TopoNets, which is from one of our former members, or actually two of our former members, where they talk about structure and artificial neural networks, how to build topology, and sort of this heterogeneity into artificial neural networks. The week before that, we had the hypergraphs as renormalized graphs, and cells as a cascade of biological machines. Those were two papers we reviewed there. And then this video that I put out 2 weeks ago on interactive morphogenesis using Moyer pattern formations to sort of as an alternative model of morphogenesis. So a lot of stuff always coming out on that channel. Right, yeah, and then as for the cybernetics and cognition futures group, those are still, we haven't had any new meetings on those. So those are still in a holding pattern. And then our open source meetings will start up maybe in about a month and a half. I'm not really sure when we'll be doing that, but probably when we get a critical mass of people to start that. Again, we've had a lot of activity in our Slack. Bradenburg Vehicle, Morgan's been posting a lot of things here.
I do post a lot of robotics in Bradenburg Vehicles, which is not necessarily in the spirit of, I mean, it's only partially in the spirit of Bradenburg.
It's fine, yeah.
But not having another channel for it. It's in there, and you know, I feel bad because it's got a lot of reinforcement learning, which again wasn't necessarily Bradenburg.
Well,
but
yeah,
there's a lot of policy work there.
Okay.
But it's good to see, you know, David Silver talking, and that's Ankur is in David Silver's lab.
Okay.
Who's doing the NeuroML GSOC?
Right.
I mean, NeuroML for GSOC project, and as well as interesting things coming out for soft robotics and perhaps swarm or multi robot control is all in Bradenburg.
So let me go up to, I don't know where we start, probably at the beginning of the year here. Yeah, so we have a bunch of work here. This cell paper on, actually, this is Device Journal. And this is, magnetic swarm intelligence and mass-produced programmable microbot assemblies for versatile task execution. And this is on swarm robotics. So that's a nice sort of extension of Bradenburg vehicle work.
Yeah. It's I like this, and I mean sometimes it's an extension of kind of, you know, that robotic control, especially for, say, kind of like a neuroprosthesis, is not as clear cut as, or the representation and the way and control can allow for very complex action. But this is definitely more in the swarm, where there's kind of a collective behavior. But these are all, somewhat of an extension like an emergent extension
Yeah.
of that multi-robot control.
Yeah. Okay. Yeah. The next one here is this. This is agent demo using PyMDP. So PyMDP, of course, is one of the things that they do in active inference. This is the Python package for. Help me out.
Yeah. This was posted, I think, on Active Inference Institute or something like that. You know, the Markov decision process as a what's the right term for it? It's like it's not as expressive a model as active inference, but this is at the time where, so we got another textbook meeting for the San Francisco Cognitive Science Reading Group on Tuesday, and I'm looking for more. I'm looking for the simple, you know, like toy problems that we can learn from.
Yeah.
And so that's why that demo is there.
Okay. Yeah.
And again, these relate, or you know, I really like the active inference discussions that are that set it in the context of like model-free reinforcement learning.
Yeah.
As yeah. So yeah. Anyway, that's again. I could find a better way to organize links.
Oh no, it's fine.
Okay.
That's fine. I think we need to go through them more often to see where we can put, you know, like, you know, it's like kind of we get the stream and then we can farm out everything into other kinds of papers and presentations.
Yeah.
Okay. This one here is science robotics, I believe. Counterfactual rewards promote collective transport using individually controlled swarm microbots. So this is swarm intelligence and like sort of count reasoning, things like that.
Yeah. As well as it is somewhat relating to, you know, again, following a lot of Active Inference Institute work, where Daniel is always bringing up ant examples.
Yeah, because he's an ant person.
Right.
Yeah, so this is I guess this is the paper, or is this like the summary? Well, this is the editor's summary, so
yeah.
Sometimes they do the summary articles.
No, totally.
Okay. Swarms of agents working cooperatively can perform tasks more efficiently than individual agents working independently. Microbot swarms have been widely used for a range of applications. However, controlling individual robots within the swarm is challenging. Hough et al. Present a control strategy for individual micro-robots in a swarm that relies on multi-agent reinforcement learning. And the learning process rewards individual micro-robots on the basis of their contribution to the collective performance. The propulsion of the individual micro-robots is controlled by laser beams, and the authors demonstrate the potential of the swarm to collectively transport cargo similarly to ants. So this is the ant sort of they have ant swarm optimization or ant optimization as like a subset of swarm intelligence. So it's interesting that, you know, they're kind of drawing from that literature specifically. So it's creating policies for reinforcement learning.
Right. Multi-agent ones.
Yeah. Okay. The Mech Lab is morphology.
This is Josh Bongard's lab.
Oh, okay, yeah.
So I think this was maybe around the time when he restarted his evolutionary robotics course.
Yeah.
And he's I think on lecture 14 now.
Okay.
I gotta say, yeah, neurotech stuff has caused me to fall somewhat behind in my lecture viewing. So I think I'm still on 10.
Yeah, yeah.
But he's still continuing his class. You know, I love the fact that he puts everything online, and like I think we talked about this time, you know, it was actually in a talk that he gave to Texas Tech. He's doing so one, he's also the Anthrobots Xenobots guy.
Yeah.
And the work that he's doing with Mike Levin, he is simulating. He's doing the same biological robot work in simulation, making predictions, and then generating that biology. And in his example of the Anthrobots is reproducing the simulation, or it's matching the simulation. So he's getting sim to real transfer from a biological simulation. So his evolutionary course is mostly discussing or simulating mechanical robots, even if they're potentially soft mechanisms. But yeah, I think it's awesome that he's doing biological simulations as well. And that's the most interesting for the kind of organoid work. Or like, again, there's so few groups that do the kind of biological simulations that he's done. You know, so it's the groups we've talked about, like James Glazier in Indiana and Morpheus Group in Dresden, and Tissue Forge, which is kind of a group of institutions. Anyway, great lab to focus on. Lots of resources.
Yeah. I think we talked about Chris Reed's lab, collective behavior, before.
Yeah. I forget what the context was, though. How it came up. Did I see him give a talk?
Maybe, could have been.
Anyway, who does he publish with?
Let's take a look.
Sorry, I just to remember.
Yeah, looks like a lot of things with ants. Yeah, a lot of Physarum work as well, which is the slime mold.
Oh, yes. I think that's I think that's what it was. It was an active inference institute talk. It was a Cambridge guy talking about slime molds and philosophy.
Oh, right. Yeah, I remember that.
Yeah, sorry. Just helps with the context. Thank you.
Yeah, actually, I see several interesting papers. This one's interesting from an ant perspective. This is learning and behavior. Ants find shortest paths using simple local rules. So we have, of course, this ant optimization, ant colony optimization method. And the idea is that ants will build these networks of trails based on pheromones, and they'll use it to locate food or some other, activity where they're trying to navigate the space. So this is, I guess, I don't know what this is, if this is like a response or like a summary of another paper. This is Garg, PNAS in 2023. Built simulation models to understand how turtle ants collectively find efficient paths for branch networks, highlighting the importance of bidirectional traffic, leakage of ants at junctions, and the ability to increase flow as key components for efficiency. Their findings provide new biologically realistic mechanisms that could improve applications in our own engineered networks. So this is where they have some very specific points about these networks, these branch networks, thinking about like something like a highway system or a system of pipes or a system of wires, and these sorts of things that need to happen to kind of make for efficient networks. It's not just about finding the shortest path. So it's interesting. And then going into specific examples from the turtle ant and talking about that. And then he talks about ant colony optimization algorithms, which are primarily designed to find efficient paths through complex networks. In the ant colony optimization approach, a swarm of virtual ants walks randomly between nodes in the network. The amount of pheromone each agent deposits is inversely proportional to the length of the path that they traveled, and shorter paths instantly receive a greater amount of pheromone. A new cycle of exploration begins with the virtual ants favoring the strongest pheromone trail, reinforcing it in turn, and the cycle continues until the shortest path is revealed. So this is, I didn't think about this before, but like there is a reinforcement learning aspect to ant colony optimization. And this would be, of course, this multi-agent reinforcement learning type of paradigm.
Did he also put something in the chat about ant colony optimization and traveling salesman problem?
Yeah, so there's also this book that has a good explanation of ant colony optimization and how it can be used to solve the traveling salesman problem. Book name is Deepak Kameni, or the author's name is Deepak Kameni. So thank you for that link or the suggestion. Yeah. So this is let's see. Yeah, this is from Chris Reed.
Yeah.
And then the ROS is the robot operating system.
Yeah, that's just somebody talking. A veteran of Willow. What was it called? Willow Garage.
Yeah. This one here, mastering diverse domains through world models. This is a
that's the most recent implementation of the world model that we were talking about. That is kind of referenced in the Adam Safran RFP.
Yeah. So this is not like for large language models. Like I think we were talking about that last week, but this is for just a general world model for, I guess, a wide range of applications. I mean, it looks like a lot of visual processing, or building it for like video game models. Robotics. So they have a research paper here, which is this mastering diverse domains to world models on the archive, and they show their performance. So this graph here actually is interesting.
Minecraft diamonds, okay, because that's a complex, or you got to make lots of different objects to get up to the diamonds.
Yeah.
Right.
Yeah, so I guess what they're doing here is there's a control task, proprio control, Atari 100K, B Suite visual control, Atari 200M, and Crafter, and they have the different, I guess, I don't know what these different algorithms are, I guess.
Older dreamers, or or some other approaches.
All right, so those are basically the benchmarks. And then this Minecraft Diamond, which is where it needs to learn this task of mining diamonds in Minecraft and getting the, I guess, This is, I guess, maximum performance is in black, and then the mean performance is in gray. So they always highlight the maximum performance. And then applied out of the box, Dreamer V3 also learns to obtain diamonds in the popular video game Minecraft from scratch given sparse rewards, a long-standing challenge in artificial intelligence for which previous approaches required human data or domain-specific heuristics. So again, it's this world model where you build a model of the world. You want to try to build a model. We talked about definitional problems with the idea of a world model as being like, what is a world model? Is it, sort of a schema or a conventional schema from artificial intelligence, or is it something like maybe a set of rules, or is it something that emerges from interactions between agents, and then they use that as sort of a guide, sort of a world model. So we talked about those in the context of large language models. This is not large language models. This is a different sort of a reinforcement learning based world model. So this is nice to have the contrast between the two. So these are the visual domains. This is the control suite, where it looks like they're doing a lot of robotic simulation. The Atari game environments, where you have these 8 and 16-bit games where you're doing simple tasks, running towards a goal, trying to hit a ball, and shoot at have first-person shooters and things like, or I guess third-person shooters and things like that. So this is all in the Atari suite. Then the DM lab, where you're navigating spaces, and then Minecraft, which is this immersive simulation, or I think a 3D simulation, more accurate way to describe it. So you have this transition from these two-dimensional environments in Atari to these three-dimensional environments in DM Lab and Minecraft. And so, having this sort of, we're training it on a sort of world, going from a 2D domain to a 3D domain. It helps. Sometimes you need a 2D domain. Sometimes you need a 3D domain. You need that extra information. And, we don't get like true three-dimensional information from these simulations. I guess in Minecraft, you navigate forward and backward. But, it's like if you were to transfer that to a real-world task, like a robot operating in the real world, it may or may not transfer. So, but anyways, what is constructing this world model? Is the algorithm taking like a detail for detail account of that world? Or is it just taking like heuristics or features of the world and using them as guideposts and generalizing from there? So, you in these three-dimensional environments, you need this sort of spatial and temporal reasoning. So you need to figure out if you need to go forward or backward. If you're in a specific situation, you need to understand when things come first, when things come later. And so that's what they mean by sort of world model, is this having this spatial complexity. Two-dimensional environments are spatially complex, just not in the same way three-dimensional spaces are. You have, I guess you could call them four-dimensional spaces if they include time. And you have this spatial and temporal reasoning, where you have things that go forward and backward and, are diverse in space, or are heterogeneous in terms of space. So creating a general algorithm that learns to master new domains out of the box without tuning would overcome the barrier of expert knowledge and open up reinforcement learning to a wide range of practical applications. So they're really trying to impart expert knowledge into these models, and separate from a training context. So, if we train the model on some data, it's separate from this world model that it acquires. Because like if you think about when humans learn, we can learn new situations, we can learn new contexts. Or in fact, we're always learning new situations and contexts. We have this world model that kind of, we kind of integrate a lot of that into. The next thing. So that was, and I think we covered some of these things before, maybe in a different channel.
Yeah, maybe.
So this is Minya Huang. Welcome to the Deep Reinforcement Learning course.
Yeah, so I think this was just an example at the beginning of the year when Josh Bongard's course was starting. I was looking for some additional, like what were the other freely available resources, and Minha here had put together the Hugging Face Deep RL course. We've talked about the OpenAI spinning up resource that is now quite old in RL terms.
Yeah.
And then of course the Coursera course from Alberta, which is based around the Rich Sutton and Barrow text, I believe.
Yeah.
Yeah.
Okay, that's good. So that's Hugging Face has a deep RL course. I didn't know they ran educational stuff.
Yeah, and so I don't know if I've actually dropped this in here, but I just caught I think it was last week or maybe the week before, but Hugging Face has a guy who's former Tesla, excuse me, who's runs Le Robot.
Oh, okay,
and,
yeah.
So this is like a project inside Hugging Face now to produce a really accessible robot arm that you can use for tasks, and as well as kind of like what's good RL policies for such an arm. That again, I love that you can do the overlap with Josh Bongard's work is cool. And again, trying to find something that that we can then take to the next level, which is like, imagine moving the arm, and decoding that, and then how to connect that imagined action together with the robot. So that's a second like interesting problem, and not necessarily as kind of linear as you might imagine.
Yeah, so imagined actions, of course, are not the same as world models, but they do kind of feed off of each other, because you have to have like a model to imagine from, I guess.
Well, it's yeah. I mean, I think it's interesting. I think that you get something like that, though, in that I think you'll start to use neural networks that have an understanding of dynamics. That's in the neural representation decoding. So there's a really interesting paper from UCSF, and I can drop links, but of a guy controlling a robot arm, but with a invasive implant, and I think it's interesting to see what how to open up kind of fine motor control from that recording. Anyway.
All right. So that's good. This is an article from NASA, demonstrates software brains shared across satellite swarms. So this is more stuff on collective intelligence, swarm intelligence.
Yeah.
This is Uncertainty in Contact with the World. This is Aaron Johnson. This is a RI seminar at Carnegie Mellon, where they're doing this. I guess this is more world model stuff.
Yeah, as well as that. well, just the kind of sim to real transfer problem that comes up because your world is not so clear. So you might have cameras that are looking down at the ground and trying to make guesses about contact strength and tensile strength of materials that you're stepping on, right? But it's just some interesting, again, real world problems for these models and how to better how to better plan for them. This also again comes up in terms of neuroprosthesis. So the people making like artificial legs, find that the more bidirectional information that they can enable in these prosthetic legs allows for much more complicated, much more difficult terrain to be managed, or for a person to be able to walk faster. So this is actually really important stuff in terms of making good prosthetics.
Yeah, that was the I think this was the paper where they talked about the Chris Reed paper, Ants Find the Shortest Paths. It talks about these different components in turtle ant colonies. Bidirectional traffic is one of them. So that's bidirectional information.
Yeah.
And so that's interesting. But that's of course another example. World models, definitely outside the realm of like simulated models into the real world. This one here is Robot Learning 2025. So this is again deep reinforcement learning and robotics. This is a playlist from YouTube, I think.
Yeah, it was a meeting.
Okay. Yeah.
So it's or sorry, they say it was a course, and maybe so, but it was I thought it was like maybe 8. Anyway, but yeah, but definitely like foundation models for all of this. And then this is the Luma is somebody speaking from that worked on the Da Vinci robot, surgical robot.
Okay. Yeah.
Which has a lot of really interesting constraints on it. Obviously, you're doing surgery.
Yeah.
So so they've got some tolerances as well as just like super fine motor action. And these are robots that are doing all this fine micro vascular work as well as like they're sewing you up.
Right. Yeah, and you don't want to make too many errors or have like a world model that's vague, I guess. Well, you wouldn't really necessarily need a world model for a surgical robot because the thinking would be that it would be very highly specialized. On the other hand, you need to have, for exceptions, you need to have an ability to kind of think outside of the task. But yeah,
it's. I mean, I think it's interesting to think what does world model mean, or because it's like in the Dreamer case, I think they were defining the world model network as the model that, given an action, what would be the consequences.
Yeah.
And I think you kind of need that. It's like when the needle goes in, that there's going to be a larger scale deformation of the tissue, kind of thing. Like for instance, I'm not sure, but again, like I love these examples for the lessons that they had to learn from experience, or from their particular domain. And
Right.
so it's like, what did the model not give them out of the box that they had to
Right.
they had to think about? Yeah.
Yeah. So in large language models, of course, we talked about world models as being a sort of causality, or like taking you in a large language model, you're constructing sequences of tokens and you're putting them together and they make sense or they don't. And then like you also want this causality, so the model knows if something makes sense to have one thing and then the next thing, and having those kind of relationships where if you construct a sentence, you usually have some model of causality. So if I want to describe something in the world that I've seen with language, then I have to put a sequence of words or sentences together that kind of where another person can follow the action. So it's like you don't want to just kind of give instructions in a jumbled way that don't make any sense to another agent or another person. And so there's that causality that you need to master, and that's above the sort of the learning that you get in putting tokens together, or how to put tokens together. Then, of course, in this case, we have sort of consequences, which is, of course, causality. We've talked about counterfactuals again, which is a form of causality. So I think there's this causality aspect to world models that I think maybe ties together a number of these different cases, if you're building them in large language models or reinforcement learning, or, robotics, which sometimes is reinforcement learning, sometimes is ant colony optimization. So you would have these world models, basically tying those together. Yeah. Oh,
but it's again, it's super. I mean, so one, I think that also gets at why, so many of these groups are emphasizing multimodal models now.
Yeah.
And because it's like maybe, like language doesn't capture all of this.
Yeah. Well, yeah.
Despite all the texts that have ever been written.
Yeah.
But I think of that example that somebody posted where kept on asking ChatGPT to fill a glass of wine and show me a picture. I don't know. Have you seen this example?
No, I haven't.
Yeah. Anyway, it's just back to Bender and Marcus's point. Is that like we focus, or we use leaderboards on the successes, but there are clear failure modes, and what we should be seeking out are the interesting failures.
Yeah. And
the revealing failures, to understand like what's missing here, because there's still something significant missing.
So that's we talked about the AI-driven robotics club, surgical robots, OpenX embodiment, robotic learning data sets, and RTX models. That's a GitHub repository.
Yeah.
Okay.
So this is it came out of somebody's talk. Maybe it was David Silver's. Maybe I think it was somebody else's. But it was a big. This is a big conglomerate, and putting all this stuff together again, trying to get at why it's still hard to get a robot to pick up a ball, and yet we can get them to write our papers and pass medical exams.
Yeah. Paper. This is the paper. Yeah. It's a paper, is a blog post of code.
But but it's easy to OpenX embodiment collaboration.
Okay. Yeah.
So it's like this big,
All right. So yeah, there's a data set. And so the abstract for this is large high capacity models trained on diverse data sets. has shown remarkable successes on efficiently tackling downstream applications in domains from NLP to computer vision. This has led to a consolidation of pre-trained models, with general pre-trained backbone serving as a starting point for many applications. And they ask, can such a consolidation happen in robotics? So this is where, we're thinking about non-robotics data sets, non-robotics context, but then robotics, where you're having to do things in the real world and manipulate things. That's a different sort of domain, and that's why they're doing this project. Conventionally, robotic learning methods train a separate model for every application, every robot, and even every environment. So we have like surgical robots, or we have like some sort of, where a robot has to run across complex terrain, or where they have to spatially navigate. Those are all different sort of training regimens, different sort of methods for doing that. And so, if you were to build a robot that was a general purpose robot or generally intelligent robot, you would have to do a lot of work in integrating all these different worlds, because robots are usually very domain specific. Can we instead trade generalist X-robotic policy that can be adapted efficiently to new robots, tasks, and environments? So here, they provide data sets and standardized data formats and models to explore this possibility in the context of robotic manipulation, alongside experimental results that provide an example of effective X-robot policies. We assemble a data set from 22 different robots, collected through a collaboration between 21 institutions, demonstrating 527 skills and over 160,000 tasks. We show that a high-capacity model trained on these data, which we call RT-X, exhibits positive transfer and improves the capabilities of multiple robots by leveraging experience from other platforms. So I think they have this image, if I can zoom in on the image. So this is, I'm going to focus on this here. So they have 22 embodiments, so the 22 different sort of shapes or phenotypes for a robot. They call them embodiments. They have 527 skills, so they have pouring, stacking, route. I think, was it last week we talked about the stacking and so there's a data set where they do stacking and then they do like piles, and they have to pick from one of those two. And there's a whole subfield on like stacks and piles and that sort of thing. So that's it's an interesting area to get into, looking at how they deal with how robots learn from their environment and the kind of data sets that they use.
I like this in particular because it matches the philosophy behind the Moab project, X, which is the big mother of all BCI benchmarks.
Yeah,
and it's the same thing where it's just like, it's like if you train on kind of one data set, you certainly in isolation, you can start to just pick up a bunch of idiosyncrasies from it. Yeah. And you really want to train across a whole lot, collected in a whole bunch of different ways, and collect it with a bunch of different equipment.
Yeah.
And then you're getting something that's much more general and much more applicable to new situations.
And then you have embodiments, ways in which you kind of have your phenotype or ways in which you can manipulate the world. You have your skills, which are these different things: pouring, stacking, route following. And then these data sets, which have attributes, objects, and spatial relations. So these are just breaking down, like, I guess if you have like a skill like pouring or stacking, there are a lot of sort of tasks within pouring or within stacking. And that's where you get these different aspects of the environment: attributes, objects, and spatial relations. So, I like this kind of organization here where we have, we kind of this hierarchy of thinking about embodiment, going from the shape of the body or the shape of the phenotype to these different skills, which are, a lot of them are very different. And so you have to kind of think about all these different, of course, you don't want to just think about the skills that we define as, kind of a top down definition. You might want to think about all the contexts in which a robot is. So there may be skills that we don't recognize currently. I mean, all sorts of skills that, like, people have a lot of skills, for example, that are hard to really kind of put your finger on what they are. And sometimes there are skills that are very obscure. Sometimes there are skills that are very obvious. But, like playing a certain sport, that's a skill. Is that something that transfers to some other motor activity or some other strategic activity? Or, is it something that if we don't invent the sport for it, you would never know you had the skill for it? So skills are kind of an interesting category because we can define skills from the real world, but there are many skills that you can have that kind of lead from this world model that you might need in some unseen context that you can then apply, but you have to have the model for that. And then you have the data sets, which include all these tasks that you might do in pouring or stacking. So you might stack flower pots, or you might stack boxes, or you might stack marshmallows, or you might stack dimes, and they're all the kind of different variations on that skill. So this is OpenX embodiment data set. They kind of break down their scenes, their trajectories, and aspects of the data set. And then they kind of show what they're doing. As a robot is asked to route a cable, pick an apple from a top drawer and place it on the counter, pick up the orange fruit. So it's doing these, kind of fine motor tasks. It's identifying objects, and it's identifying like shapes and colors. And so it's using semantic labels. So it is multimodal in that sense. That you have motor learning, you have sequence learning, procedural learning, you have semantic learning or language learning, and then you have the instructions, you have the images, you have this transformer, and then you have these discrete actions, and then that's where the actions are executed given the sort of the learning of these things and the processing of the information. All right, moving on. This is the Towards Superhuman Intelligence talk by David Silver. So we talked about David Silver earlier. What did you want to say about that, Morgan?
Sorry, I was muted. He, very well known as being the person who did the DeepMind RL course, right? Yeah. Sure, or certainly the lecture series that DeepMind released. This is the kind of expertise that he's coming from. At this particular conference, oh yeah, okay, Vidhi's used those too. And so when I saw this particular talk, I was curious where it fell in how we're going to achieve this mythic super intelligence. Yeah. Or I mean, so when people are using superhuman, they're saying that, like, they're still saying that, like, we've achieved superhuman performance on Atari, right? For instance. I think it's interesting that there hasn't been as much follow-up on how the game of Go has changed since AlphaGo. right?
Right.
But like humans have started to play differently.
Yeah.
And I'm not saying that necessarily means that they can take on well, perhaps they could, or certainly you see this, you see, yeah, there's a difference in play. Anyway, it's I wanted to see how nuanced this particular talk would be, or if it was, if he's fallen into a certain I'm a marketing mouthpiece for my global conglomerate.
Local
and
conglomerate.
back
Yeah.
to again Bender and not just Bender. Cory Doctorow's point that like these companies have every reason to lie.
Right.
like their stock price, their immense personal wealth, all dependent on you thinking that these are superhuman.
Yeah.
And that tech companies are capable of waving a magic wand, right, and making making science available from your smartphone.
Yeah.
Right. And yeah, anyway,
so superhuman is defined as like above human performance on tasks.
And it gets to this debate that like what's his name, Hinton and I made.
Yeah.
Not that I'm putting myself in the same camp, but I made the same mistake in the sense that like I was just like, oh God, I was amazed in 2012 before ImageNet, working in radiology, about how radiologists worked, and I was super surprised that radiologists don't use pseudo color imaging for looking at grayscale data, for instance, right? So if you go to UCSF, like top 10 kind of hospital in the country, and you go to one of the radiology reading room suites, these are dark rooms with very expensive grayscale monitors, very expensive screens optimized for viewing these kinds of images. And I was just like, well, it doesn't matter what they spend on the screen. Their eyes could only handle like a certain number of levels of gray. Right. Like, what's the screen matter? And as someone who's gone through the kind of training that satellite imagery people have, in Colorado, like military satellite analysts do not limit themselves to the particular the particular data that they receive, or like if they've received well, just that point, right? I mean, part of it is that they moved, they do deal with what they call hyperspectral imaging. So frequency is a much larger dimension for them because they're collecting data from infrared through, right? And so they're actually typically looking for ways to do some sort of dimensionality reduction across frequency, and then to match like say the top 3 principal components to red, green, blue. So what you're looking at is yeah, it is not. It is not color.
Yeah.
Right. You're looking in eigenspace, or yeah, you're looking at um, eigen components, or well, principal components matched to color, because sorry, this is the final point, because your eye is the perception. This is what you're trying to get it
Right.
set up as as an input for, because for this perceiver system, and it just seems like radiology was right for a better way of doing it.
Right.
And so that was the famous Hinton, like 2015, I think, like radiologists will be out of radiologists will all be out of business in 5 years or something like that. Right. I forget what his time frame was, right? But I definitely said the same thing to myself, and said the same thing in terms of just like, why don't they add color to these images, in terms of using algorithms to find interesting things, and then to add color to those things, for instance. Like, again, like, it just didn't make sense that you still had people reading them like they were reading x-ray slides.
Yeah.
But we're here, like I mean, I keep seeing these examples, but I'm sure, like, you might follow somebody like Eric Topol. Have they've not taken on the medical market, and even though you keep seeing these examples where it's like they outperform a radiologist on a very limited dermal cancer task or something like that.
Right. Well, I mean, that's interesting from a cognitive model and computational neuroscience standpoint. Is like, what are we doing in terms of like processing an image in terms of our brains, and then what could a computational model do, like an artificial intelligence agent? So, like, what are they using? Are they using eigenspace? Are they using like CIE values? And then, like, how does that translate to performance? So there's some breakdown of the sensory information. There's some internal representation of that, or internal sort of transformation of that, and then there's a performance output. So if like a algorithm is using like a complex eigenspace versus like our eyes are using like some sort of differencing of color or whatever, or not using color at all, then of course that might explain superhuman performance. Whereas if maybe the methods are sort of maybe the methods that we're using are superior to what an AI is using, and that goes of course to world models, but also to this sort of Gibsonian type model of processing. Exactly. Yeah. So I'm thinking about this.
I mean, that's I thought it was super interesting that the satellite imagers were, in a sense, setting things up for pop-out effects.
Yeah.
Right. So it's just like they seem to know intuitively or not that you want to transform your data to the point that humans get pop-out effects of the things that you want to pick out, which made me like rocket launchers, or whatever it is. Yeah. Right. And so
I'm still thinking about this, so we'll come back to this later. Yeah. So I mean, we had something else in the chat. Oh, this is a YouTube video here that was put in there.
Yeah. That's the playlist of the DeepMind RL, David Silver's course.
Okay.
it could be pretty old. I mean, like 2018 or anyway, but like but it's one of those that it might be in Minha's list of good, RL resources.
Yeah.
Yeah.
All right. So then, let's see. We have building robots at home. Some other robotic seminar stuff. This is things from the Maker Lab at Illinois, SIG Robotics at Illinois, and then Physical Intelligence.
Yes, this is a group, and I'm assuming that they're maybe like former OpenAI people or something.
Right.
But Physical Intelligence is its own group, and OpenPy is their model.
Yeah.
Or yeah, hit that. Is it a team at OpenAI, or is it their own company?
I think it's their own company. I can't.
I think it's their own company, and it's probably again, it's and it's like it's a whole bunch of VCs and Jeff Bezos. Okay.
Yeah.
Anyway, but this definitely comes from the really awesome Buzz Robot group in terms of speakers. So Buzz Robot gets great. I wish I knew how she got so many great speakers, but she's the one who got the Robot guy just a couple weeks ago, and then this was the talk like a month or like a couple weeks before Robot.
Okay.
Yeah. Oh, and then Aloha there, right? So I think we talked about this, but that this is what I think his name's Remy from the Low Robot guy. This is the paper that he said was the real breakout for manipulation, arm manipulation.
Okay.
Yeah.
All right.
So the novel action chunking. So it just again wonderful overlap of cog-sci, robotics, and machine learning.
Yeah. All right. Then finishing up, Aloha. That's the link to the repository.
Oh, gotcha. Yeah.
All right. Yeah, and it looks like Vidhi joined the Brainwave Vehicle channel. So.
I forget what Lakiwi is, but I think Remy has a post since his talk about some Lakiwi developments, which I assume is like an added a more complex little robot. Yeah.
Okay. All right, so that's good. Thanks for that. That was a pretty good discussion on the Bradenburg Vehicles channel, sort of unpacking all the stuff in the channel. And I think, we've talked about world models, but it's like there's a lot of stuff there. There's like these kind of conceptual models. There's like, world models for different types of artificial intelligence, different types of learning. We have multimodal models and all this. So I think, definitely going down that road some more.
And just for Vidhi, if you might also check Dev Neuro AI, because again, sometimes I don't know where best to put some things, but related topics could potentially robotics and other things that might be important for that discussion. Yeah, Dev Neuro AI. And it somewhat reflects the discussion that that Jess or the meeting that Jess posted on developmental Cognition, I think, was the group name that met in Boston.
This is the one that
I think in general.
Or in general, yeah, it was in general. That was the one here that just posted the other day.
Yeah.
So this is on YouTube. This was a meeting that was yesterday. It's on developmental, I think, psychology, like developmental psychology, developmental things. So
cognitive development.
Yeah, cognitive development. There's Jesse right there. And yeah, so I don't know if Jesse had anything to say about that. I don't want to put him on the spot.
Yeah, I would love to. I'd love to hear.
Yes, I may be able to say. Well, no, I can say a little bit now. In short, I've been around ekkolapto for a while, but I haven't really done any. They've hosted a number of events, like here in Boston, other places too, and they're kind of coming. And it sounded like Morgan knew more about them, or some of the people there, which is, I know of them through my experiences, but not that much. And it was just nice because it was sort of, it actually was, and sort of like one of our longer, or like a long open-ended meeting on a subject topic that we do. And sometimes, so it ended up being the first one, I forget what it was about entirely. I guess it was the polymathematical one. And then there's one yesterday also about kind of developmental approach to cognition, and it was a lot about plasticity, but also dovetailed into a nice conversation around sort of I'm saying the word wrong, but hormesis, the one that's like a small change creates an impact and you come back from it and then it like overcorrects or something like that.
Hormesis, yeah. I think,
yeah. And so a lot of in essence, the Polymathon was kind of a warm up for their events next week. They have a number of very big events, cool events. Michael Evan will be virtually attending to one of them, but a lot of things in Florida. A lot of the group is based out of Florida Atlantic, and there's an event there next week. I think two different events. I'm not going to be there, but the first one was kind of a warm up for that, and it was a nice, well-rounded discussion about where could it was quite broad in some ways, but some of the focus topics were on like where can what would a futuristic hospital look like, and how would it go from what a hospital is now to what limitations may change in time, which is interesting in the context of the moment we're in terms of healthcare right now. But it was good, and it was that was part of it. And then yesterday was interesting. Addie, who's sort of the founder, or I don't know the right word to say, but the person leading these salons and in a lot of the direction of where things are going there, for sure, has a very interesting take on like synesthesia and kind of this interest in how different sensory interactions either complement or can lead to enhancements. Like there's a number of things that were talked about that kind of fit in the space of kind of essentially biohacking type stuff. But I really enjoyed all of them, but I enjoyed the conversation yesterday too, in the sense of getting at a broad level of what either in an agent or a system what's sort of the line between perturbance and detriment or deterioration, or like just enough agitation or stimulus to provoke useful changes. And that was sort of a nice overlapping theme between the two. I think there's also another one today. Like there's a series of like small, of these like salons or big discussions they're having, and what I can say here also is that there's a few like specific projects that they're trying to push forward, and there's a little bit of overlap too. I would almost say as a group similar to us in that they're very interdisciplinary focused and okay with exploring some of the niche spaces and sort of this um, the challenge of doing that, the challenge of how much like you would even uh, we've kind of evolved to this meeting is just a big Saturday meetings of this, it could be anything, and then we've branched it off into these more focused discussion groups. This is sort of what we've done to handle that, but they're still sorting out what they want to do in certain ways and what pillars do they want to focus on, and oh, they are selecting for that and have a lot of really interesting people who are doing interesting projects and other things that I think we'll hear more of publicly sooner. But I've really enjoyed their events, and it's it is different in that they're trying to host and do events differently and a different set of structure and different set of things here, but a lot of the actual respect for trying to pursue inquiry and not being afraid to throw, as Eddie says, like wrenches into questions and the sort of openness to uh, like really trying to get in and out of a topic and really shake it up is interesting and nice. So I don't know. There's a lot of small things that could be said about specific topics and things like that. One of them I was very much reminded of our previous work on like I think it was something like developmental freedom and then developmental whatnot. One of the questions that came up with the plasticity one was essentially how much is too much plasticity and why do we need plasticity? And I think I shared something and took this a screenshot of one of my quotes, and we didn't really go down this route, but I immediately thought of like a lot of our developmental work, um, kind of operating in these boundary constraints of when an organism is developing, yeah, when an organism is developing, you have this. I go back. I go back to one of my first like neuroscience actual experiences in a lab where I was trying to understand, at what lab, at what day of being alive does a in this case, a mouse or a lab mice have start actually showing a circadian rhythm in development, and all these questions about like, well, it's not right away, because certain structures have to emerge and develop before things can even synchronize to it, and obviously many different species are different, diurnals or this or not, different kind of rhythms, but just sort of like at a bottom up level, the necessity for things going on. I think I did well, and the other end of the spectrum was, but the other side of that is like the, you know, the death, the inclination towards, okay, well, you know, maybe in an evolutionary sense, well, you're this, you know, you're no longer very good at producing stuff and you just need to get out of the way. So we're gonna, you know, start showing you the door in terms of your maintenance. And that's one way to say it. But sort of this, my main point, which I think I did not articulate very well and probably won't do here, but it's something that we have talked about a lot in our like cognition futures and the memory and a lot of developmental stuff is sort of how um, there is just uh, there isn't a static um, um, things aren't static. There isn't a static thing. There isn't a static cognition. There isn't a static state of being. There's this constant movement and constant, you know, very you know, um, what are the qualities of being alive? You have, you know, you're taking things in, you're letting them go, you're changing, and it's sort of like that's quite obvious in some ways, but it's almost like a lot of discussions around these topics tend to be um, I don't know. Um, Very centered on speaking as if like the mind or the brain, even though we're talking about plasticity, is like just this sort of uniform chunk of play that everybody has the same, you know, model of. And it was sort of fun to kind of tease out um, these different takes on what's influencing that. But um, and then finally, I'll kind of say it was interesting to basically look at and this is the one yesterday I'm kind of concluding about, but you know, the age old question, or you know, it kind of reminded me of similar to that, like how we talk about in this lab or have for the last few years, um, analog versus digital kind of a thing. Like this gigantic um it's not a debate. I don't really know what to call it, but just sort of how do the things relate or not. And it kind of felt a little bit similar to that. It's obviously not the same topics, but the way of the question of like the plasticity question and in a kind of a neural sense, yes, but also at is very like what about the body too? What about like muscle and there's other things that basically would perturb in this case. It was mostly biologically focused here, but some things that perturb a system and yes, how much, but also sort of what are the there was a nice arc of the conversation that I kind of wish materialized a little bit more, but basically about what is too much plasticity or why do things need to be not plastic at times. And that's kind of where some of our work on developmental freedom versus developmental, like I forget it was capacity or something else, made a lot of sense to me because like you have to do that. Also, last particular point of interest, there was a really interesting conversation the day before, which actually more so fit in this one, but came up in the wider ranging like polymath medical one, which is about don't have great language for it right now, but it was essentially how it was sort of about, you could say attention or focus, but how when you are like I think one of the people cited a bunch of experiments in chess and how the more trained in chess you are, the less actual like there's a weight to your memory over time, and like you don't think of or remember invalid chess moves as easily as valid ones. So it's like I said, oh, so it's like you have more nuance, you know, and there was like, oh, actually it's less. He's like, no, actually it's less nuance because you have less overall nuance, but more. I think the word was synthesis and like a greater refinement of what you can do in the context of things that are right or valid chess moves. But the mind kind of cancels out the things that don't um, aren't valid, and it's sort of sign of an indication of like sort of how the expertise of something, like if you speak English all the time, you kind of tune out invalid ways of pronouncing things. But if you go to another language or from another language, you can hear or speak differently, um, in a way that challenges that kind of going into um, the more specified, nuanced things. The more specified, I would say, detailed things, and the lack of a broader, um, decontextualized nuance, I would say. And so um, that was sort of an arc of conversation that I would imagine would continue to the next event, which I think is today, and I may or may not be able to go to it. But point being, it was a nice, these salons as they have been so far have been these sort of big broad ranging things, and I think they're kind of adjacent to some things we've talked about, and if people want to go to them and invite some of the topics that come up, I can see about that. But I think they're going to have these are they don't just do salons. They've done like some hackathons and some things here. There's one here at the MIT Media Lab, which I didn't get to go to, but inadvertently met some people there and stuff through it. So they're doing a lot of fun stuff, and we'll see where they go in the future. So, any questions? I know I did a lot of conceptual bouncing around, but yeah.
No, I think that's some good stuff to follow up on.
There was
yeah,
obviously
especially
quite a bit more, but I kind of
yeah,
selected for things that we kind of
especially some of the concepts that like you tied it into developmental freedom and some of these other things that we've done in
yeah.
papers and that, and that might be more, it might be interesting just to do a paper on developmental freedom and kind of revisit that concept and kind of lay that out in terms of artificial learning, animal learning, etc. Um, and we'll have to come back to that. I think that's really great. And this whole idea of like, learning and adaptation and kind of how those merge together with development, and
Yeah.
this is something that is kind of always interested me, but is more generally kind of, it's like this huge topic that people have kind of approached from different angles, and it's kind of
Yeah.
hard to get your arms around what to call it, because it's kind of like it, you have adaptation, you have development, you have learning, you have plasticity, and they're just kind of all these things operating, and like kind of stitching together a unified theory of all this is hard to, and having these kind of concepts where we can say, oh yeah, that's something that applies to animal learning, but also to artificial models, and kind of
Right.
think more deeply about these forms of learning, and that's I think that's valuable, but it's people haven't spent nearly as much time on that as maybe we should.
Right. And I kind of I mean they're very familiar with Michael Evan. He's this, going to be a speaker at an event, and they had people from Levin's lab at stuff at events, so they know about him. But also, I mentioned a little bit on diverse intelligences, and even Dizzy, the Summer Institute, and it's just like, yeah, like, nobody. I think I even said as much. Like, at once it's like nobody really cares. like people do care, but it's not um, profitable or useful to enhance things as they are right now.
Right.
So, and that's a harsh and a negative stance. but yes, like it's I always enjoy being able to talk with people that are kind of aware of those. Here's a space, that could go in a certain direction, and are willing to kind of try to. We had a very nice like sub conversation about like how do you create environments for people to do the work that lets their I don't know, try to make progress on these things. It's hard to do. Like we've talked, like even like our twirly bird stuff and that whole thing we said about like that conversation across time. Like you kind of have to, you have to like create enough stability in the conversation in the group over time to do the work to make like my vantage points essay, which I don't know if I ever really shared here or not, but like you have to do this work of just building out vantage points and trying to connect them and so on and so forth. So it was sort of nice to talk with another group in this situation, and quite a different group in terms of some of what they really want to focus on in the short term, and maybe other things, but overall, like quite sympathetic to what he said and those challenges. And yeah, I mean, it's so funny because I've known about them for a long time, and as we know here, I haven't been around much, and I'm coming out of this winter of sorts, metaphorically and literally. So it was kind of a nice set of warm ups and things to do and ways to talk about, and we'll probably have things ahead. Maybe in the future, some kind of an overlap of efforts between the groups, but at the very least, very interesting people doing very interesting things, and more ahead there.
Do you know what the name of the group is?
Yeah, ekkolapto.
So this is the ekkolapto. This is, I guess, a group, experimental interdisciplinary research group focused on modeling and enhancing general cognitive systems. So their website is here. Science, art, stronger together, and they have cool smells, really smart people. They have these, I guess, different groups. Yeah.
So yeah.
They have a cognitive hackathon, a new salon. I guess that's where they do the talks. New vision, polymath. Yeah, this is really interesting stuff.
Yeah, and Addie's the person you saw in the video, like yeah. Yeah, you can see some of their events down there. Like they've had things in like around Florida Atlantic, as you can see the FOU. And then kind of host. I think they're in a period of like doing a bunch of these salons recently, and then next week is a bunch of events in Florida, and they're kind of, they kind of there's not like I don't know. I don't really know. I'm trying to speak like I know them very well because I don't. But it's not quite the same as like we have this standard meeting every weekend. They have sort of I don't really know if I could say a cohort, but a collection of people interested that have a lot of deep relationships about certain things, and meet regularly and put on events too, which is pretty cool.
Okay, I think I know who these people. This is Florida Atlantic. Elon Holtz is one of the people here involved. So yeah, this is good. Yeah, it's interesting. It looks like it's very very new and exciting stuff.
Yeah, I think a lot of good things will come from them. I'm happy to. I met them through Dan Elton, who is long time. Dan and I grew up in the same hometown, and then both went to Boston, and then he left Boston, and Dan's did a lot in AI and healthcare spaces now, and we kind of I don't know. I kept having all these misses with ekkolapto in person, like last fall and summer, and I'm sure I'll be dealing with some more things down ahead. So good stuff, and I very appreciate being invited to um, go to the events and share things and have like conversations. I found it on a personal level, like I found um, it's very important to to stay in touch with people and talk about things that are interesting and things that do have meaning and can affect the future. It's sort of like my self-care is to intentionally do it, and there are a great community for that with people that care and are thriving. Similar to we're doing that here too, and I'm very glad to be back here with this group more so, and appreciate our conversations as well. I think it's maybe even a public good on some levels, but a good for me for sure. So
Yeah. So Trevor Tanner, he posted this paper on cell genomics paper on effects of gene dosage on cognitive ability, function-based association study across brain and non-brain processes. So
Yeah,
this is go ahead.
I know David Glenn there.
Okay, yeah, David Glenn. Okay, so this is the graphical abstract. Trevor's interested in behavioral genomics and cognition and things like that. So this is where they sampled 258,292 individuals from the general population. They did a cognitive assessment, plus they did this genomics study. They were looking for copy number variants, which are where you have a certain number of copies of different alleles, and you look for the variation across people, and you correlate it with things like cognitive assessment or sometimes phenotype. They use these gene-wide association study type approaches where you look at the CNV, the copy number variation. Then they have this functional burden analysis, which is where they have a biologically defined set of genes, where they look at whole body tissue genes, brain region genes, brain cell type genes, and they use Go terms to sort of define this. So this is the annotations, that typical annotations of genes that you find. Then they have this, so for this gene set, they have an effect size, which is based, roughly related to cognitive ability. They have this result where they look at, it looks like there are two classes here: confers protective effect, or increases cognitive ability, and then they look at the effect of gene set on cognition, or the effect size of a gene set on cognition. Ian Brief reads, copy number variants are major contributors to neurodevelopmental disorders and are associated with lower cognition. Hough et al. Identified a duplication increase in cognitive ability. They highlighted that genes of many biological processes had unbalanced gene dosage sensitivities towards deletions or duplications for both brain and non-brain functions. So they're looking at this group of people, this large group of people. They're doing a cognitive assessment. They're doing a gene-wide association scan. They're looking for these copy number variants. They look at the copy number variants in terms of deletions and duplications. So sometimes you can miss or sometimes alleles are deleted, sometimes they're duplicated, and then you look at those two classes, you annotate those genes, and then you look for different reasons why they might be duplicated. Does it increase cognitive ability? Does it confer a protective effect? And then you look at the effect size on this gene set on cognition. So you look at what deletions and duplications give you, and this tag DS method, which let's take a look at the abstract to learn more maybe about that. So yeah, copy number variants that increase the risk of neurodevelopmental disorders also affect cognitive ability. So this is where we have variations in copy number of alleles that increase the risk of neurodevelopmental disorders. So sometimes you have things that are sort of, duplicated that affect cognitive ability, but also set of neurodevelopmental disorders. So, that's the kind of thing we're looking for. We're interested in that. However, such CNVs remain challenging to study due to their scarcity, limiting our understanding of gene dosage sensitive biological processes linked to cognitive ability. So what we'll want to understand is how does gene dosage or number of copies of an allele, how does that link to, it's involved in these biological processes that are linked to cognitive ability. We performed a gene-wide association study, or GWAS, in 258,292 individuals, which identified for the first time a duplication at 2q12.3 associated with higher cognitive performance. So they were able to identify a specific copy number variation associated with higher cognitive performance. We developed a functional burden analysis which tested the association between cognition and copy number variation, disrupting around 6,500 gene sets biologically defined across tissues, cell types, and ontologies. That's where they were annotating the different genes and cell types and tissues. Among these, 864 gene sets were associated with cognition, and effect sizes of deletion and duplication were negatively correlated. So this is where they had the scale. The latter suggested that functions across all biological processes were sensitive to either deletions, so this is the subcortical regions and postsynaptic related genes, or processes, or duplications, cerebral cortex presynaptic processes. So we have deletions and duplications being associated with different things going on in the brain. Associations between non-brain tissues and cognition were driven partly by constrained genes, which may shed light on medical comorbidities in neurodevelopmental disorders. So it's a nice study, goes over a lot of technical stuff that I'm not going to get into, but this is an interesting link between genomics and cognition, and some of the things that are driving like the evolution of cognition and developmental disorders. So again, this is a little bit beyond what I want to get into here, but
well, I think it would be good to say that it's behind perhaps subtle but complex structural differences.
Yeah.
Or you see what I'm trying to hedge here,
yeah.
or you're like, but as well as like, at what level is it operating?
Yeah.
This was interesting. So, I've done work with David Glenn on bipolar disorder.
Yeah.
And I mean, in terms of brain imaging.
Yeah.
Right. And I don't think we did anything genetic. But so this was interesting to see, though. I'm glad Trevor passed it along, because it's an interesting little rabbit hole down psychiatric genetics.
Yeah.
But again, like I more and more lean towards psychiatric genetics as like, or brain structure, structural composition and physiology in a kind of Michael Levin, like, I mean, in the sense that how responsible is genetic control over organogenesis?
Yeah.
And etc. But it's a I'm just seeing some papers here from, looking at the large ABCD data set, which for some reason has a registered trademark sign. Like, why does it like ABCD is an NIMH thing with like it's got a.
Well, I think that people just do that sometimes to. I don't know.
That's frightening. Anyway, I'll figure that out later.
Yeah.
But but as it relates to cognition, I mean, as well as this, as well as these points that come up in psychiatric genetic, or they're more likely to come up in psychiatric genetics when people are trying to explain why these things could be selected, or like evolutionarily, how did we get here?
Yeah.
And as opposed to, just as opposed to putting them in a. I guess I like the context that Levin has, where everything's imperfect and everything has cognition.
Yeah.
or like everything has agency, or anyway. Yeah. But yeah. So nice. Thank you, Trevor.
Yeah.
And yeah, if anybody wants to go down these rabbit holes, my college doesn't have a lot of scientists from it, but I had one. It was Pamela Sklar, and her focus was psychiatric genetics. So she was my hero, because she was the one putting together these larger and larger data sets that included schizophrenia, and in terms of trying to, what Sam Barandies calls the gene hunting, right? So, in my youth, we sought the genes responsible for schizophrenia, and what I, anyway, she passed super young, so we don't get to see her conclusions on this, but I think we ran into the much bigger question of organogenesis and kind of epigenetic factors that Levin has highlighted, that are so important for how we get complex tissue and organ structure.
Yeah.
And especially one that is molded, and then I loved all the discussion that Jess had around plasticity, and the kind of the tension that you have in plasticity, where it's like you want a learning system, but you want a learning system and you want a memory system.
Right. Okay, that's good. Yeah, thank you again, Trevor, for that contribution. This is an interesting. Let's see.
Everything.
Yeah. So I think we talked about this in a previous meeting, where people are putting the video game Doom on very small devices. So this is an article from IGM. The weirdest devices that can play Doom, including a Lego brick and an ATM. So this is something that we talked about in previous meetings, where people take the video game Doom and they can load it onto things like a refrigerator or an ATM, things that don't. I mean, they have a lot of memory compared to the original version of Doom back in 1993, but they, it's like people are amazed that you can play them on these small devices, so-called small devices. So there's this whole kind of cottage industry of people. I don't even call it a cottage industry. It's just kind of a hobby will it run on Doom? So this is a long-standing challenge where modders and programmers attempt to get the game to run on any device imaginable. When you ask the question, will it run Doom? The answer is more often than not yes. And we talked about this in a previous meeting that it's a fairly small program. It's Turing complete, and so there's an interest in running Doom on things because if you can run it on relatively low-powered hardware, you can do a lot of interesting things with simulating world models or simulating other types of things. And so that's a nice compact program that you can run. So below you'll find a list of some of the wackiest devices that can run Doom, with visual and gameplay quality varying greatly depending on the gadget. So people are running it on things like Lego bricks, refrigerators, an ATM, TI-84 plus calculator powered by potatoes, which is kind of a side. It's the calculator. It's interesting. And of course, these are all kind of, not, I wouldn't say low powered devices, but lower powered devices. So if you think about, like, if I want to put something on microbot or, some other type of thing, we've talked about running large language models on things like a Raspberry Pi. We did some demos a long time ago on that. So that's interesting from that standpoint, that you can run these, potentially high-powered computational systems on these relatively small devices. So and you can play Doom on a rotary phone, apparently, on a NordiTrack treadmill. So this is like the treadmills now, of course, they have displays.
That's not a surprise.
Yeah, that's not a surprise so much. And then you have a digital camera. This is an iPod Nano. Again, these aren't like super low powered devices. They're just kind of things that you can do, and people have done this with like doing things in Excel spreadsheets and all sorts of things like that, where you can really kind of feel like the original Atari games, for example, where people were highly constrained by memory. So they had to program games in like this very small buffer of RAM. And so they had to kind of get creative. And that's kind of the idea behind these challenges, is that you can get have a very relatively small buffer and create these worlds within them. So apparently someone also put Doom on a pregnancy test. And again, the pregnancy test has like a small display, but it has a decent amount of computational power, especially compared to the hardware we had in 1993. So yeah, and you can play Doom on a PC running within Minecraft and other things, in VR for rats even. So that's kind of this idea of running Doom on everything.
I'm upset that again we've lost our Slack history, and my it runs Doom examples have disappeared down the rabbit hole.
Yeah.
But I every time I see one, I post it in random, and and yeah, it's I don't know why it became. I mean, I don't know if it's just it reflects the fact that like for so many of us of at least that particular generation, Doom and Quake were seminal games, as well as like certainly Carmack's superpower as a programmer was to get so much from limited hardware.
Yeah.
And like a lot of his engineering was around tricks you could play to get more realistic activity from limited constrained systems, but
Yeah.
yeah, that's always funny.
Jesse had a comment. This is almost like a variant of read-only memories 2064.
Well, yeah, and I say that quite loosely, but that game's come up a few times in different ways, and those that don't know anything about it, it's a I don't know. It's a cute game about the future and about kind of cyberpunky themes. But in the game, you sort of get at one point, semi-spoiler, but not really. You kind of get a point of like, oh, what are you going to do to resolve a certain crisis? And you basically you basically get to like heavily limit what a lot of AI entities that are sort of robots and are artificial intelligent agents. You get to limit them, or you get to sort of almost like put a whole bunch of like you could make like a toaster and all these things that aren't really fully sentient, if you will. It's sort of like arbitrarily you get to choose if those things are arbitrarily sentient or not. And it's a very interesting thought game, and in a similar way, there are references in the game to kind of more than just like, oh, like Quake and Doom. But there's references in the game for people kind of growing up, kind of, I think, slanted towards like probably millennials. Like there's references baked into it that are interesting in a similar way. So it's just a fun way to think about it. Obviously, a limited operation classic video game isn't the same as or is it? But it isn't necessarily the same as I don't know, fully expressive sort of human level sentience, just dropping that into a toaster or a refrigerator. But it made me think about that. And there's also another segue. I don't know. I think you're finished with that, but something I will say in Slack more that I'm looking into is around the gaming topic, but especially for those with certain disabilities. So stay tuned for some discussion about that on the Slack, and kind of if people are seeing this or you're watching this and you think about, oh yeah, Jesse's looking for games about people with different kind of like accessibility for people with various disabilities, reach out to me about that, please.
Yeah.
More about that later.
Yeah. Well, I think I want to make 2 more points about this. First of all, I remember, I think it was back in the cybernetics meetings, we did a series of meetings on the Levin and Bongard paper on
Oh yeah, and living
sentient
machines. I mentioned that. I actually
Yeah.
mentioned that paper this week in the other discussions.
Yeah.
Yeah.
So in that discussion, we kind of, I think I made a point about like what they were getting at was like, we have machines now that aren't like, we have the machine metaphor of the brain, and
Right.
but then we also have machines that are kind of like artificial brains, and they were trying to work out a taxonomy towards between like machines, cognition, and then cognitive machines. And it was interesting. It's a hard paper to write, but I think I made the comment, or I made the comparison there with like a sentient toaster, or it was like something like that. And you mentioned toasters, and it's like taking like some behavioral thing, or in this case maybe like a world model, and putting it on a machine. The question is, how much hardware do you need? What's the size of hardware do you need to build like something like a world model, something like a sentient program or whatever? And can you put how small can you make that? How do you get the, because there's also the issue of an animal brains, where we have all sorts of hardware. We have C. elegans connectome, we have worm or other types of anoid connectomes that are even smaller. What are they doing, and what level of a connectome do you need to have like really complex behaviors, world models or whatever? So I think that's interesting too. This relationship between processing constraint or architecture size and these kinds of self-contained programs that can do things, interesting things. The other thing I did want to point out in my notes, and I had my notes here. So I asked the question, or actually it says, I have these questions that are kind of phrased. So I talked about that article, and one of the questions asked, will it run Doom? So like, will something run Doom? You can take any piece of technology or maybe even a connectome and say, will it run Doom? And from the article, we know the answer is that for fridges, TypeScript, ATMs, older calculators, rotary phones, iPod Nanos, the Nordic Track treadmill, within Minecraft, an instance within Minecraft, and digital cameras, the answer is yes. We could assemble a list of maybe no's, and we could also include like animal connectomes in this as well. And then the second question is, why does Doom run on everything? And then asking Copilot and asking R Gaming, the Reddit group, and then I can find out more about why does Doom run on everything. So Copilot's answer is Doom's engine is a medium detail mode that triples the speed of the game on slower machines, making it a hugely accessible game. This, combined with its internal shareware release, has made Doom run on everything. Fans have gone to great lengths to rig and tinker with unusual devices, such as digital cameras and microwaves, to make Doom run on them. The sheer imagination and engineering skills on display when it comes to getting Doom to run on improbable platforms is impressive and keeps the game relevant today. The R Gaming answers, and these are people giving feedback. You can run a lot of other games in many unconventional ways. It just happens to be a mean to make Doom run on everything, maybe because of a quote or something. Of course, not all variants of Doom you might have seen are the same source code, simply because of size limitations or graphical limitations. So again, the source code size is important, but you can run other types of games as well that have the complexity of Doom. Someone else said it's literally just for the memes. Really old, so insanely light, code so small it can run on anything. Plus one of the most famous games of all time. Don't need much more to make it a phenomenon. It's light now, but the joke is back in the day it was hard to run in some cases. I had to do various weird things on my computer to get Doom working. My mom was so mad that I screwed up my computer when one of her friends reconfigured a bunch of stuff so Doom would run. It was a Packard Bell 486 SX33 with 4 megabytes of RAM. This other answer, it was unique in the way it was made. When it was made, it was a game that visualized 3D gaming before computers were ready for 3D games. The reason for it to be ported to anything is a mix of the source code being public for modding and the fact that the game is a 2D game looking and playing like a 3D game. The real reason Doom was and still is an awesome game, and Doom is the grandfather of all shooters today. So then there's this article here, not can it run Doom, but can Doom run it? This is this article here. But can Doom run it? And there's another blog post on that. How large is a Turing machine if needed to run Doom? So this is a question about how large of a Turing machine is needed to run Doom. So this is a question about, like, if you flip the question and say, what size Turing machine do we need to run Doom? So this is a Reddit post on this. And so, there are a lot of interesting computational questions here. A lot of interesting things that, lead to a lot of the questions that we're talking about
today. Yeah. I think it's important to emphasize that it's source code that is also why everybody, it's source code and it's just so much damn fun.
Yeah. And then Jess said, it's like a slightly techie modern will it blend or will it float? Okay, so to finish up, I'm gonna talk about this. It's kind of an esoteric topic. I don't really have an answer to this, but It's about closed loop feedback and machine learning. So I've gotten a couple of articles and screenshots of things. So this is like something I was interested in for the stuff that we've been working on with respect to cybernetics and closed loop constructs. This is an article. I think it's some documentation I got from Jeff Holton. This is from 2019. This is machine learning. Closed loop intelligence is a design for machine learning. So this is an article, and so this is basically talking about taking closed loop closed loop systems, closed loop motifs, and using them to use as a design pattern in machine learning. So there are many great articles on using machine learning to build models and deploy them. These articles are similar to ones that teach programming techniques. They give valuable core skills in great detail. But to go beyond building toy examples, you need another set of skills. In traditional systems, these skills are called things like software engineering, software architecture, or design patterns, which are approaches to organizing large software systems and the teams of people building them to achieve your desired impact. This article includes some of the things you'll need to think about when adding machine learning to your traditional software engineering process, including connecting machine learning to users, what it means to close the loop between users and machine learning, picking the right objective, knowing what part of your system to address with machine learning, and how to evolve this over time, implementing with machine learning, the systems you'll need to support a long-lived machine learning-based solution that you wouldn't need to build for a traditional system, operating machine learning systems, what to expect when running a machine learning-based system over time. Of course, the first question is determining when you need to use machine learning. One key factor in the decision is how often you'll think you'll need to update an application before you have it right. If the number is small, for example, 5 or 10 times, then machine learning is probably not right. But if that number is large, say every hour for as long as the system exists, then you might need machine learning. So it talks about these different aspects of implementing machine learning and whether it's right for you or not. But this idea of closed loop feedback is kind of talking about closing the loop in different contexts of applying machine learning. So closing the loop is about creating a virtuous cycle between the intelligence of a system and the usage of a system. As the intelligence gets better, users get more benefit from the system and presumably use it more. And as more users use the system, they generate more data to make the intelligence better. So you give the example of a search engine, and then, but a successful closed loop doesn't happen by accident. In order to make one work, you need to design a UX that shapes the interactions between your users and the intelligence so that they produce useful training data. Good interaction has the following properties. The components of the interaction are clear and easy to connect. The outcome should be implicit and direct, have no or very few biases, and does not contain feedback loops. So this is interesting in the context of this closed loop system, which of course is where there's a connection between a user and a machine, and there aren't feedback loops within that. So the closed loop can suffer from feedback that compounds mistakes. For example, if the model makes a mistake that suppresses a popular action, users will stop selecting the action because it's suppressed, and the model may learn that it was right to suppress the action because people stopped using it. So having feedback loops within that closed loop is not optimal. It's interesting because we think maybe of more feedback being better. But you can, so to address feedback loops, an experiment should provide alternate ways to get suppressed actions and consider a bit of randomization to model input. There are some of the basics connecting machine learning to users. Machine learning will almost always be effective when the UX and machine learning are designed to support one another. Doing this well can enable all sorts of systems that would be prohibitively expensive to build any other way. And then this is a section on intelligence orchestration, which is kind of leveraging both users and machine intelligence. Intelligence orchestration is a bit like car racing. A whole team of people builds a car, puts all the latest technology into it. It's every aerodynamic wing, ballast, gear ratio, and intake valve set perfectly. They make an awesome machine that can do things no other machine can do. And then someone needs to get behind the wheel, take it on the track, and win. And then intelligence orchestrators are those drivers. They take control of the intelligence system and does what it takes to make the machine achieve its objectives. And so this is kind of reminiscent of Ashby's intelligence amplifier idea, where it kind of goes through how people use machine learning systems and optimize them through, different behaviors. So the Ashby's intelligence amplification stressed the idea of, maybe the machine has more intelligence than the human, maybe the human has more intelligence than the machine, but it's a symbiotic relationship. And so, it's like leveraging the best of both worlds. And we've seen this implemented in something like hybrid chess, where humans have been beaten by artificial intelligence at chess. So what chess players did in response to that was leverage some of these artificial intelligence systems to hone and refine their strategies of playing chess, using machines for things like, look ahead strategies, and then using what humans do best, which is implementing the strategies, and using that as a symbiotic system. And, minimizing the amount of negative reinforcement and positive, maximizing the amount of positive reinforcement. So this is an interesting article here. Here's some other screenshots I took of a Quora discussion on this. So this is where they asked people, in what ways do closed-loop feedback systems resemble machine learning techniques? So this is not how do you implement closed-loop feedback in machine learning, but it's a question of how do they resemble standard machine learning techniques. So some interesting comments here. Let me get this size here. Okay. This one is, in a control context, ML is not feedback unless you consider recursion feedback. ML is a more recursive adoption to a static or slowly moving model. Sequential least squares or Kalman filtering or kernel filtering are all recursive. So it's introducing this concept of recursive feedback. So it's like in machine learning, you have recursion. In programming, in programs in general, you have recursion. And that's sort of the level of closed-loop feedback that we may consider. Control includes, among other things, like robust control, adaptation of slowly varying parameters while controlling an external process with its own significant dynamics. This control comes in the two flavors, feed forward and feedback, to modify the behavior of some external process, which would be outside the computer. So it kind of talks about traditional control theory, where we use a plant model to manage the current state, and you have this feedback that occurs with disturbances, and then there are objectives like estimation and control. So you have a plant that determines the current state, there's feedback on the current state, of the world, you have some disturbance or non-disturbance, and then the plant has to estimate or control the current state from that information. And so that's a very typical standard way of thinking about control theory and applying that to a machine learning context and implementing that through recursion in a program. This answer here is also interesting. Is there any relation between control systems and machine learning? So this is a little bit different way of phrasing it, kind of leading up from control systems, because we've established that control systems can be programmed into a machine learning algorithm. You bet there is. I'll start with the basic building block of modern machine learning paradigm, the perceptron. This was a hardware structure built in the 50s by Rosenblatt to mimic the real-world neural network in our brains. It arose out of control theory literature when people were trying to identify highly complex and nonlinear dynamical systems. Neural networks, artificial neural networks, were first used in a supervised learning scenario in control theory. Hornick, if I remember correctly, was the first to find that neural networks were universal approximators. You've heard about the classic sigmoid nonlinear activation function used in machine learning, deep learning as a nonlinear squasher. It came out of the control theory literature. Without classical control theory, you could say that there would be no backpropagation, which is a Rumelhart and Hinton innovation, which had inspiration or its basis in control theory. There would be no backpropagation through time, which was a 1990 paper by Warbos, backpropagation through time, what it entails. And this is now used in recurrent neural networks by modern machine learning practitioners. There would probably not be this LSTM method, which was invented by Hough in 1996, which is used to model tap delay lines in memory-based neural networks. These have found massive use in speech recognition, language models, and time series sequences. The conflict between exploration and exploitation in reinforcement learning is known in control engineering as the conflict between identification or estimation and control. And so this was by Witten in 1976. So this goes back not only in machine learning, but in reinforcement learning as well. And of course, we talked about sort of these behaviors in human machine systems where you have this tension between human performance and machine optimization. And so this actually, the reinforcement learning example here also ties that to control theory and other things. So that's an interesting, I guess Andrew Ng's thesis featured this reinforcement learning control theory slash closed loop feedback relationship as well. If you read the works of modern machine learning theorists, you'll find control jargon camouflaged in new diction to make their ideas sound new or sexy. So this is where we're kind of in putting new wine in old bottles. I think there is some sort of disingenuity among these researchers by not acknowledging that these algorithms arose out of a domain they are not often willing to give credit to. So when they call it backprop, it's nothing more than old-fashioned calculus-based differential chain rules. So yeah, there is a lot of stuff that is kind of repackaged, but comes from that traditional sort of control theory background and maybe further back from cybernetics. And so, is there any relation between control systems and machine learning? This is the same question. So this person says, kind of. Machine learning algorithms, especially neural networks, are used to approximate functions that cannot be hard-coded. The approximated functions map one set to another set. For example, the mapping function between cat images to the cat category is, the sort of we want to approximate that function. Control theory does research for similar types of functions, meaning the mapping from one set to another set. But the sets are different between the machine learning and control theory examples. In control theory, the input set is a set of signals, or the series is transformed, Fourier transform can be found, and the output is also a set of signals, or just a signal. So, they're talking about like if we had a set of images versus a set of signals. Major differences between the control theory and machine learning examples is that in control theory, most of these functions can be found analytically, meaning that there's a direct way to find the desired function. You solve a set of equations, you reach the function. However, in machine learning, there isn't any analytical solution that we know of. You have to approximate it. There are a few maybe, but you can't use them for most problems. This is why machine learning problems are approached as an optimization problem, where you have to approximate the answer. And you have to really spend time finding an approximated function. You have a lot of iterative discovery, trying to find local and global maximum on a landscape, which consumes time, and the function cannot be proven to be resistant to adversarial inputs. In control theory, this means the closed loop control system cannot be proven to be stable. So the methods that we use in machine learning especially like gradient descent. Those things are not, those things are different than what we do in control theory. So it's an interesting relationship between the two. And of course, in control theory, that's a more like real world focused instance of closed loop control. So now, of course, these two areas intersect, but this answer basically argues that analytical solutions are kind of the key to understanding this relationship. So there are two other additional papers I want to talk about here. This first one is machine learning, deep learning, and closed loop devices. This is in the domain of anesthesia delivery. And, so this is an applied method for looking at closed loop systems, applying machine learning, putting it in the loop. And so this has been going on in anesthesiology since the 1950s. And so this is where they're trying to automate the delivery of volatile anesthesias based on different types of data like EEG. And then, of course, people have been developing closed loop methods in this area for a while, trying to find ways to develop methods for delivering neuromuscular blockades, and other types of, like, physiology, of course, is dependent on real-time sort of delivery of anesthetics that work in that way. The classic open loop control system in anesthesiology target controlled infusion devices in which a hypothetical plasma or effect site concentration is targeted based on estimations from a population model of drug distribution and effect, was kind of developed in the 1990s and is now a mature technology. So they kind of go through some of the closed loop innovations in anesthesiology and how AI can improve those. And, they kind of get into a lot about closed loop systems and their definition here, where they define closed loop systems as acting to maintain a given variable at a desired set point by three key elements: a sensor, a controller, and an actuator. So of course, we think about in cybernetics, we think about this more broadly, and we don't make the distinction between like an automated system or an artificial system, and if you're interacting with something like a physiological system, how those two things are related. Because in physiology, of course, we have the concept of homeostasis, and we have these physiological systems which are in homeostasis. But we also have then this closed loop between an artificial system and a physiological system, which also has to maintain this sort of homeostasis. And so we have these concepts: sensor, controller, actuator, and we have to apply it in different ways that fit the system we're looking at. So that's this paper on anesthesia. I think it's an interesting example of, like, in a specific domain where you have sort of regulation built on top of regulation. This last paper is from Cell Reports Physical Science. This is merging machine learning and bioelectronics for closed loop control of biological systems in homeostasis. So this is what I was talking about, where people are thinking about these bioelectronics or biomechatronic systems and building artificial intelligences inside of them, but then scaffolding them on top of existing biological systems, which have this sort of also this physiological regulation going on. And you have to sort of, it adds to the complexity of this closed loop, because you have kind of closed loops on top of closed loops. And so this kind of talks about how physiological processes rely on the state of equilibrium called homeostasis, which is achieved through this biological control loop involving sensors and actuators. We have sensors and actuators in our physiological systems. That's sort of this metaphor for different types of sensory organs and other types of things that we use to act upon the world or act upon our internal state. But they can think about it in this general model. However, disease and aging can disrupt these control loops, leading to impaired or slower homeostatic mechanisms. Bioelectronic devices offer the opportunity to interface artificial technology with these biological systems, allowing people who have diseases or have aging issues to retain that function. So if we think about, neuroprosthetics, that's one example where you could recover function, homeostatic function that's seamless, or attempts to be seamless with the physiology. So in this context, we propose that machine learning can significantly enhance the capabilities of bioelectronics by facilitating real-time processing of sensor and actuator data. By utilizing machine learning-driven bioelectronics, we can maintain and regulate biological systems responses more effectively compared to traditional approaches. So this advancement holds promising implications for bioelectric medicine and precision medicine, particularly in repairing impaired homeostatic mechanisms. So this is a vision paper, but it gets at what I was talking about with these feedback loops on top of feedback loops. And of course, we have this whole issue of interacting with a machine learning system. So yeah, Vidhi had a comment here. As we're wrapping up this meeting, I just wanted to say that even though I may not speak or contribute much, I've been learning a lot. So thank you for that. Also, I've been focusing on Project Idea 5 and working and implementing the chat space due to my university exams. That's fine. We're pretty far out from the deadline for GSOC, so I'd appreciate any guidance on how to approach the pre-GSOC phase. Yeah, so the pre-GSOC phase, we're trying out things. We're not quite at a proposal stage, but please send things if you want feedback on them. You can post them in the GSOC channel in the Slack or communicate via private DM with myself. And yeah, so that's okay. Yeah, thank you, Vidhi, for. I'm glad that you're getting something out of the meetings. Any comments on the papers that I just reviewed?
Mm-hmm. Yeah, interesting. So just going back to the closed loop, kind of more general discussion, and the machine learning versus control theory, yeah. I think maybe discussion. Certainly one thing, the center that it's like Nathan Kurtz and Steve, I'm blanking on his name right now. He does these videos. I think it's like dynamicsai.org. Is that it? Anyway, two things. So, like you said, or, as the authors said, control theories usually got these analytic formulations. And so this is the goal in something like symbolic regression, or and so pi SR and the similar Julia projects, a lot of cool math, or a lot of cool SciML is focused on exactly that, right? Like I get data, I crunch it, and I get out an analytic equation, right? And this is come up just super. So now then to the anesthesia examples, like that's particularly cool, and of course super relevant for me. One, it's interesting that there was a 1950s EEG sensor-based control loop, closed loop. Mm-hmm. That's interesting. As I've pointed out to my anesthesiology friends, why don't you use EEG?
Yeah.
That is not something that is typically monitored, which is fine. Or like anesthesia is very successful,
Yeah.
and relatively low risk. But yeah, it's the thing that came up that is actually an organoid paper from the Johns Hopkins group, like Hartung and Lena Smirnova, together with Johns Hopkins Applied Physics Lab people. And they are using zebra. Okay, so in my head, I have to say zebra and then replace the Z with a C. Okay, that's how I remember it. So you could go to zebra .ai for the approach that they're adapting, and it's somewhat related together with this idea of embeddings, that like you can find a lower dimensional space in which this problem is easier and regularized and things like that, right? And so, and I bring it up in relation to dynamics AI because I looked at this paper that is just a preprint, and sorry, I haven't been updating it on brain organoids because now there's just so many slacks. and now we've added like found some people on a Discord channel a Discord server that are interested. Shred from Nathan Kurtz. I want to say Steve. We keep it in my head. I keep saying Steve Ballmer, and it's just like,
yeah.
no, like he's in Washington. He's in UW.
Right.
But it's yeah. Anyway, but Kurtz has shreds, which I forget what the acronym is, but it's very much a it's very similar, and I'm curious now to try and talk to Hopkins about would they give us are these data sets available so that we can try shred, because I was really anyway, but it's a spatiotemporal spatiotemporal representation that again gets that ideally at the end you're going to get a kind of a dynamics equation.
Yeah.
And what they're using it for, the organoids, that reminds me of anesthesia, is that they're looking as organoids age, when do you see the dynamics change?
Yeah.
Right, because you do, or like the experience people have is that at a certain age they mature and they start to have these endogenous oscillations and other kind of new behavior. And of course this is also super interesting, or these approaches are things that I would also just like to try on high density EEG recordings and things like that.
Yeah.
So what would that give us from non-invasive electrophys? Which has a really interesting history for not only resting versus task behaviors, but also drug action and anesthesia and coma and sleep all change the overall dynamics of the spatiotemporal electrophysiology and like how to understand that. But Anyway.
Right.
And then it relates to control in terms of neuromodulation. People want to say, like if I TMS this person's particular area, I can now instill a new dynamics in there.
Yeah.
Electrophysiology. Anyway, sorry.
All right, that's fine. That's great stuff. So yeah, thanks for the meeting today. I think we'll wrap it up. And again, if you have any questions, the Slack is open, and see you next week. Thank you.
Take care.
Take care.